We're looking at rational functions today, and particularly their graphs. And so these are going to be some of the different features we'll be looking at. A lot of that we've done already. We're just going to be putting these things together on an actual graph, seeing how they come together in the graph of the function. So for domain, we need to look at when this function is undefined. So of course, that was the denominator being 0. Again, if we've got a fraction that's undefined, that means that it's the denominator, the bottom of the fraction, that's 0. So for this function here, of course, that would be x is -1. That would make this undefined. And we don't have any square roots or any other potential problems. So our domain is everything except -1. Right? Well, what happens at -1, there's no point on the graph, and so that turns into a vertical asymptote. So at this entire value of x is -1, everywhere on the coordinate plane where x is -1, there's no point on the graph. And so that vertical line of x is -1 is going to be an asymptote. So the domain and the vertical asymptote go hand in hand. The vertical asymptote is x equals whatever x can't equal. Okay? And I'll notice there's this little note about unless the factor can be canceled with the numerator. We're looking at that in class on Thursday this week. So if you haven't had class yet, then stay tuned. Or if we had class already and you missed this, you can take a look at the video. But these little stars here of this little caveat of things canceling out will be for our discussion in class on Thursday. Right, so horizontal asymptote, again, was the ratio of the leading coefficients. So as long as we have equal degrees, which we have here, we can take a look at this. And we're looking at 2/1. And so we get y equals 2 for our horizontal asymptote. Now, x and y intercepts, we haven't necessarily done these with rational functions yet, but it's just the general idea, again, of an x-intercept means that we want the y to be 0. And so, I mean, you could just set this whole thing equal to 0 and solve it out if you want. We'll be doing several of these problems. So if you want, you can just remember the shortcut, go right to the numerator being 0. Because if we want y to be 0, we want the whole fraction to equal 0. And if we want a whole fraction to equal 0, then that means that the numerator has to be 0, because again, if the denominator is 0, it's undefined. So here what we want is 2x plus 1 to equal 0. And so that's going to give us x equals -0.5. And so the x-intercept is -0.5, 0. And then for the y-intercept, of course, just like normal, that's when x is 0, so we can just plug in 0 for x, substitute 0 for x into the function. So we get 0 plus 1 over 0 plus 1, which of course is just 1. So our y-intercept is 0, 1. So then what we want to do is throw all this stuff onto the graph here. Okay, so we've got a couple points. So we've got -1/2, 0. Then we've got 0, 1. Okay. Now, these asymptotes are not actually part of the graph. They're kind of a feature of the graph. So again, what we said is 4x equals -1. There's no point on the graph. So we put a dashed line here. And so I'm using red. I'm using a different color to signify this. This is not actually part of the graph. This is a lack of points on the graph here. We're going to be approaching this vertical line without quite touching it. All right. Same thing for this horizontal asymptote of y equals 2. There's not going to be any points on the graph where y equals 2. We're going to get really close, but not quite get there. All right. And so at this point, you might be able to see what this part of the graph is going to look like. It's got to go through these 2 points. It's got to approach this asymptote, get really close to this horizontal line, get really close to this vertical line. And so this part of the graph is going to look something like that, where again, this gets as close as you want, but never quite reaches it. So at the end of the graph right here, horizontal asymptotes are always, you approach the horizontal asymptote at the ends for really large x's or really negative x's. So over here, you have y point y equals 1.9, y equals 1.99999, y equals 1.9999999, as close as you want, but you never quite reach y equals 2. So the image for our course, I'm an asymptote, can't touch this. That's the idea. We get really close, but don't quite touch it. Okay. Now there's going to be one other section of the graph here. We know it can't be in this section here, because if we had more graph here, then we would fail the vertical line test. We wouldn't be a function. And so it's either going to be here or here for a simple function like this. So one thing that you could do if you really had to graph this, without a calculator at all or anything, again, you can always graph things by just plugging in numbers, making a table, plugging in points. So we could figure a number over here. Maybe if this is -1, try -2. If x is -2, plug it in, see what you get. -4 plus 1 over, that would be -1 there. So we'd have -3 over -1. So we'd have +3. So we've got the point -2, 3. So we've got a point up there. And so probably the other section of the graph just goes like this. There'll be some more complicated ones where doesn't necessarily follow this easy thing, but often also the basic rational function, the two sections will be kind of opposite of each other. It's just kind of for simpler ones. So really, though, usually we wouldn't necessarily expect you to have the full graph without a calculator. So we might give you some matching problems where, if you know these features right here, then you'll be able to maybe do process of elimination and figure out which one's the correct graph. Or we'll give you your calculator if we want you to really accurately know the graph. So you can check this here. You can do alpha y equals to type in a fraction looks like a fraction. And so we've got 2x plus 1 over x plus 1, zoom 6. And there we go. That's what the graph looks like. Okay, again, those dashed lines are not actually part of the graph. They're kind of guidelines of what the graph gets really close to. Okay, so let's try this second one here. So for the domain and for the vertical asymptotes, we'd be looking at when the denominator would equal 0. Well, that would be when x squared equals -1. With imaginary numbers, of course, that's possible. You could say x is plus or minus I, but in this class, we're just going to do all real numbers. That'll be the case in AP Calc as well. Also, just whenever you're graphing things, a graph is all real numbers. The xy plane, coordinate plane, Cartesian coordinates, all this stuff here. If you're graphing, it would just be real numbers. And so for real numbers, that's not possible. Okay, so when is this undefined? Never. Well, if it's never undefined, it's always defined. The domain is just all real numbers. And that means that there's no vertical asymptotes. There's no places, no values of x where this is going to be undefined. No values of x that the graph avoids. Okay. Now the horizontal asymptote, remember you can only use the ratio of leading coefficients rule if they have equal degrees. And so there are rules you could just memorize if you wanted to. There's a rule for if the degree of the numerator is less than the degree of the denominator, what it would be. Or you just use my trick. Add in a 0 term. If you add in 0x squared and then look at this right here, you'll have 0 over 1, and so your horizontal asymptote is y equals 0. Now for your x-intercept, you want the whole fraction to equal 0, which would mean the numerator would have to equal 0. Well, last time I checked, 4 never equals 0, so we've got no x-intercepts here. Y-intercept, we want x to be 0, we plug it in, 4 over 0 plus 1. So we get a y-intercept of 0, 4. Okay? So we know we've got this point here, and we know that we have a horizontal asymptote here. Y equals 0 is just the x-axis. Okay? And that's all we've got. Okay? So again, if this were a matching problem, you would just be going through the different options and eliminating anything that didn't have that point and that asymptote. If we wanted to try to sketch it without the calculator, I mean, you could always plug in more values of x to find some more points, or you could try to maybe picture what's going on here. So we know at the ends, it has to approach the horizontal asymptote. Again, the horizontal asymptote is only the ends of the graph. The idea we talked about was like Bill Gates doesn't stop to pick a penny off the sidewalk. The small stuff doesn't matter. As x gets really, really large, as x starts to be a billion, these small things start to fade away. Okay, but that's only true for really large values of x. If x is a small number, then these small things don't fade away. So it's only approaching the horizontal asymptote for large values of x for these ends of the graph. So at the ends of the graph, it's going to approach that horizontal asymptote. So it's got to approach like that, and it's got to hit that point right there. Well, that just means it actually just kind of is like a hill, just like that. Okay. And again, if we really wanted you to draw the graph yourself, we might give you a calculator to help you kind of sketch, through this point and along that asymptote. But you should know at least kind of that point and that behavior at the ends right there. Right. Let's look at another one here. So this one, for the domain, we want to see first where it's not defined. So x squared minus 1 equals 0. So that would be plus or minus 1. So that's where it doesn't work. Those are the two values of x we can't have. And so the two values of x that we can't have are what creates our vertical asymptotes. Domain and vertical asymptotes will go hand in hand. Horizontal asymptotes, again, watch out for when we don't have equal degrees. If we don't have equal degrees, there is a rule. If you want to look up the rules and memorize them, there's a rule for when the degree is greater in the numerator than the degree of the denominator. I just use the trick of adding in a zero term. And so then I look at these. So I've got 1 over 0. 1 over 0 is undefined. So that means there aren't any horizontal asymptotes. For my x-intercept, I want x cubed to equal 0. Well, that's just x is 0. So I get 0, 0. And then, well, if it's 0, 0, that has to be the y-intercept as well. I mean, we can plug it in as well to double check, but 0, 0 is both an x-intercept and a y-intercept. Okay, so we've got this point right here. And then we've got a vertical asymptote on the left, and we've got a vertical asymptote on the right of that point. And that's all we've got. So again, with matching, you could do process of elimination to just figure out which ones have those features there. At x equals 1, it would have to be kind of, either shooting straight up or shooting straight down. Make sure you understand what a vertical asymptote looks like and what a horizontal asymptote looks like. We can look at this one on our graphing calculators as well. Alpha y equals. And we've got, if alpha y equals doesn't do anything for your calculator, just make sure you put parentheses around the numerator and denominator. So you'd have to have x squared minus 1 in parentheses. If we take a look at this, so we've got almost a cubic looking kind of thing there, except the cubic would go kind of out to the sides more. It wouldn't approach the vertical line, but a similar shape. So this middle section goes like that. And then on the sides, that's kind of an interesting thing here. So we approach the vertical asymptote there, and then this just kind of goes out like that. And then down here again, it's close to the vertical asymptote, and then it just kind of does something like that. So there actually is another type of asymptote that you might be able to see here. We've talked about vertical lines and horizontal lines being asymptotes. There's also actually slant asymptotes. So you could have a diagonal line that's an asymptote. There's a line right there that this graph is approaching. You can actually also have parabolic asymptotes. You could have a graph that at the ends would be looking like a parabola. So here, if we covered up the middle, that would just look like a line right there. So the middle always does funny stuff, and then the ends of the graph can approach a horizontal line or a slant line or a parabola. If it weren't for distance learning, we'd have a whole nother day on that, but because of distance learning, that's all you get on that for right now. Just know there are other types of end behavior, what we call it. Okay. But for us, as long as you can find these features here and know what they look like, if you had to do some sort of matching without your calculator or with your calculator, know how to kind of fill in the blanks and sketch the graph according to these guidelines of the asymptotes, then you'll be good. All right, so why don't you go ahead and try number 4 and number 5 here. Those are a little bit trickier. So find the features and put those on the graph, and then see if you can, probably don't even try to draw it without looking at your calculator. Just kind of in your mind, think for a minute what you think that they might look like. Those are a little bit trickier. So you'll want to look at your calculator to see the behavior of the graph. But you should be able to find all of these features yourself without your calculator, and then take a look at the graph in your calculator. Go ahead and give problems 4 and 5 a try here. All right, so this is what number 4 looked like here. Make sure you saw the asymptotes were at square root of 3, not 3. Sometimes people go a little too fast and don't realize it's square root of 3, not 3. And then for number 5, we actually did have equal degrees in the numerator and denominator. If you multiplied that all out, it would start with x squared. And so that's what this one would look like here. Now, actually, both of these graphs here do something a little interesting that you might not have thought was possible. Wonder if you thought something was wrong here. Both of these graphs actually cross their horizontal asymptote. Take a look here. We actually had an x and y intercept right on that asymptote there, and then this one crosses the horizontal asymptote right there at that point. So the whole idea of can't touch this actually is not always exactly true. You can cross horizontal asymptotes, but notice what part of the graph is where it crosses the asymptote. For both of them, it's near the middle of the graph, right? Remember what I was saying about horizontal asymptotes? They're about the ends of the graph. Horizontal asymptotes, when x is 100, 1,000, a billion, these smaller terms start to fade away. And so for large x's is when we start to approach that horizontal asymptote there. It's only the ends of the graph where we approach and can't quite touch the horizontal asymptote. In the middle, all bets are off. There's all kinds of funky stuff going on in the middle of the graph. It's the ends of the graph where it starts to approach some particular behavior.